Hello, ladies. Today we are going to be talking about resistance. It's the next section of our electricity notes. And we're going to go through a little bit about what resistance is. We're going to introduce a new formula. And it's going to be great. So let's get going. So, as charge flows through a circuit, objects like light bulbs draw some of the energy. Any component of an electrical circuit that consumes some of the electric power and converts it into whatever it may need is called a load. Okay? So a load could be something like a light bulb, right? Because it takes that electrical energy and it converts it to light energy. It could also be something like a TV or a computer, a toaster, a fan, your cell phone, that can be considered a load when you plug it in. Anything that you plug in that consumes some electricity, that electrical energy, that is considered to be called a load. So, taking a look at these 5 examples we have here, light bulb is our first one. So it takes that electrical energy and converts it into light energy. Okay. If we take a look at something like a toaster takes that electrical energy and converts it to heat energy. Okay? Because it causes the inside of the toaster to heat up, and that heat will then toast your bread. So electrical energy into heat energy. If we look at something like a fan, that converts electrical energy into kinetic energy or mechanical energy. Kinetic energy or mechanical energy is just something that is the energy of motion, right? In a fan, you have the propellers or the blades inside spinning around. So that is an example of kinetic energy. If we're looking at TV and computers, right, they would convert the electrical energy into light energy, just kind of like light bulbs do. But then we also have like sound energy or audio energy, right? Because your TVs and your computers, yes, they light up. You could see them on the screen, but they also have a volume to them as well, right? So a load can consume electrical energy and convert it into multiple different types as well. So those are just some common examples, but more exist. Again, anything that you plug in that consumes some of that electrical energy is considered to be called a load. Okay. We're also going to talk about resistance, right? So when we're talking about resistance, there's actually 4 main factors that affect resistance in a circuit, and you will need to know these 4 main factors and how it affects the resistance in a circuit. So the first thing is the length of a wire, right? If we remember back to our circuit diagrams, say we drew a circuit diagram like this. Of course, I'm going to put a battery in here and maybe a light bulb. So here's my light bulb. I'm going to do the little swirly inside. That's my personal favorite. I have a battery. Let's say it's a 2-cell battery, right? Just a reminder that my side of my battery that has the longer line, that's my positive side, and the shorter side is my negative end of my battery. And I know that my current flows from my negative terminal to my positive terminal because it's the electrons that are moving all the way around. Okay, oops, sorry. Whoop. Okay, that light bulb is a load. Now, if I have, again, this exact same circuit, but instead of just having a short distance from here to here, I increase it. I increase the length of the wire. So I have essentially the exact same thing, but now my wire is longer. Well, that means my electrons have to travel further, right? It's a longer loop. As we have the length of the wire increase, the resistance increases, right? It's harder to get through a longer path. If the path is shorter, it's going to be less work, therefore less resistance. And we can kind of see it in this cartoon here. The shorter wire, these electrons are like, ooh, so short, we can make it there. Oh, yes, life is good. Oh, easy peasy. Whereas this long wire, oh, those electrons aren't there yet. They have to keep going. The struggle is real. Right? So the longer the wire, the more resistance, and then the opposite exists as well. The shorter the wire, the less resistance. Okay? Another factor is this cross-sectional area, or you could consider it the diameter or how thick the wire is. Okay? If we're taking a look at this picture here, if we have a really thin wire, it's going to be harder for those electrons to move through. There's not as much space. Kind of think of you walking down the hallway, okay? If the hallway is really, really wide, even if there's people there, you're not going to really be resisted by those people because there's a lot of room to go around them. If that path is really, really narrow, the hallway is only like one person wide, and even if there's only one person in your way, well, there's going to be an increase in resistance. So if we have a thin wire, it's going to give us more resistance. And if we have a thicker wire, that's going to give us less resistance. Okay? So as the cross-sectional area, you could also think of cross-sectional area as the thickness. As the thickness decreases, so it becomes more thin, the resistance increases. And then vice versa, if the thickness increases, it becomes more thick, the resistance decreases. Okay? Which means as one goes up, the other goes down. Which gives us this thing called an inverse relationship, or it's something is inversely related. I wanted a different color. Here we go. So as the cross-sectional area goes up, the resistance goes down. And as the cross-sectional area goes down, the resistance goes up. We call that an inverse relationship. Another factor is temperature. And for temperature, as temperature increases, so something gets warmer, it gets hotter, the resistance decreases. So as our temperature increases, our temperature rises, our resistance decreases. Resistance decreases. And as our temperature goes down, our resistance increases. And you could kind of think about it as if we had, some sort of material in which electrons were flowing through. If we heat it up, those electrons are moving faster and they're faster and they're faster and they're faster, and they could kind of run by and scoot past things. So yes, there are still objects that might be in their way. They might bump into them, but they'll still get through that path more quickly. Okay. If we chill things, we cool them down, the temperature decreases, those particles aren't moving as quickly, so when they bump into something, it takes them quite a while to get around them and move past. Okay. So similar to our cross-sectional area, temperature and resistance are also inversely related, which means as temperature goes up, then our resistance goes down, and vice versa. As temperature goes down, our resistance goes up. Okay? Our last and fourth one of the factors that affect resistance is our type of material, right? So you might have heard of different types of wires. Wires are made of different types of metals, typically, because remember, metals are good conductors. So we have different types of wires, and the wires, some of them have more resistance than others. Just because the shape of those metals, if we think about their atomic structures, what an atom of that metal looks like, each atom is going to be a little bit different, and that's going to affect how the electrons can flow through them. So if you're thinking about things like, I don't know, nickel or aluminum on our periodic table, right, they're going to have a number of protons and a different number of electrons, so they're going to have a different atomic structure, and that different atomic structure affects how the electrons move through. So there's not necessarily a rule of thumb in terms of which metals will always be better than others. So it's more so just an idea of testing things out. Some metals do in fact work better than others, some's not so much, but we just know that that will affect the resistance in a circuit. Okay. All right. We also have things called resistors. Okay, so a resistor is something that provides resistance. And it's actually a particular device. And this is what a real-life resistor would look like. Oops, sorry. Zoomed in by accident there. So this is what a real-life resistor might look like. So if you have an electrician come into your home and they're putting in resistors, or they're doing the wiring in your house, or maybe they're building something, maybe you are tinkering and trying to take apart your toaster and put it back together, and you might come across something that looks like this. This is called a resistor. And what a resistor is, it is a device that is used to create an electrical resistance within the circuit to limit the current. Okay? So in a circuit, you have the flow of electrons over time, right? The amount of charge over a period of time is your current. Sometimes, if your current is too high, that could actually get your device or your circuit to overheat. And that could actually cause some severe destruction, right? That could cause fire or damage to your device. So having something to reduce that current is really important. And that's where our resistors come in. So a resistor, again, is a device that is used to create an electrical resistance within the circuit to limit the current. So it's going to slow down that flow of electrons within your circuit. The whole purpose of it is to regulate the power that could enter the device, right? You don't want too many electrons to get in there at once or too quickly. It does this by limiting the current flow through the circuit to prevent overheating and to prevent the destruction of our devices that are connected to that circuit, right? So if you have ever maybe traveled somewhere, particularly in Europe, for example, they have a different current that comes out of their outlets. And so very often, if you go to Europe, you'll need an adapter that'll adjust the current. Because if you plug in your device directly, that could actually cause your device damage. So sometimes it'll just reduce your battery life. So you might have a shortened battery life and it's not going to come back after time. Or it might actually cause your device to overheat or things like that. So having resistors within your circuit, really, they're just there to protect your device and to protect overheating and especially fires, in terms of, like, if you don't have resistors in your home, then we can get into electrical fires, and that's never fun. So overall, resistors are used for protection, operation, and current control by regulating the power that can enter the device. All right. We are also going to introduce one more formula today, and that is our resistance formula. Okay. Luckily, our resistance formula actually already uses two other variables that we've already introduced in previous lessons. So here we have the resistance is equal to my potential difference or my voltage. Remember, they're synonymous. We could say potential difference, we could say voltage, they mean the same thing. Divided by my current. Okay, so if we said that in terms of symbols, resistance is symbolized by the capital letter R. We know our potential difference, or our voltage, is with our capital letter V, and our current is with our capital letter I. Okay? So our resistance is actually going to be measured in ohms. Okay? And ohms is another Greek letter. And to draw that symbol, you kind of draw like a flat line, almost a full circle. Oops. Come on. There you go. Full circle, but we don't really close it at the bottom there. And then another flat line at the bottom. That's the ohm symbol, and it's spelled OHMS. Okay? That is the unit we use for resistance. It is a Greek letter. It's not an English letter, as I'm sure you already know. But that is, like, if we said resistance, we could say, oh, there is 6,000 ohms of resistance. Okay? Potential difference is measured in volts, right? Remember, it was named after Alessandro Volta. And our current is measured in amperes or amps with our capital A. Okay? And we're going to be using that formula. If you are a fan of that kind of triangle method that helps keep you sane here, to help you rearrange the formula in different ways, we know that we have R is equal to V over I. Because I said V over I, V has to go at the top. I will then have to go on the bottom, and R will then take up the empty space. Okay? If we are trying to figure out all of the different formulas we can get, of course, we have R is equal to V over I. We know that because if we cover up R with our finger, we are left with V over I here. We can do this for all the letters. So if we cover up or cross out V, we are left with R times I. So V is equal to R times I. I realize now I should have probably erased that first and then done that, but R times I. And lastly, if we want to figure out what I is, we have V divided by, or V over R. Okay, so we have I is equal to V over R. So those are our three different rearrangements of the formula. We will not provide you with this triangle. The only thing you will get on an assessment is the original formula here. So you will need to know how to rearrange that formula to give you this guy in this guy if need be. But again, that triangle is a nice place to go ahead and rearrange things in a super simplistic way. Which one did I erase? I is equal to V divided by R. All right. I believe we have 3 examples here, and then we're gonna be done. So if you don't have your calculator out, feel free to do that now. You are more than welcome to use a calculator on any sort of assessment here. And we're going to follow the exact same 4 steps as we used for every single one of our previous equations and our work that we do. So here we're going to read the question. We have a speaker is operated by a 9-volt battery. Only 0.006 amps of current pass through the speaker. What is the resistance within the circuit? Okay. So we start off by listing everything we know and what we want to find. So here we're starting off with 9 volts. And we know that voltage or potential difference is measured in volts. So we would say our voltage is 9 volts. Next we have 0.006 amps. Okay. We know that our current is measured in amps, which means my I, current, is represented by the letter I, so I is 0.006 amps, and we're looking for my resistance. So my resistance, come on, hello, resistance is some value, some value, and my unit's going to be my ohms. So again, remember, that's my step 1. I am writing out everything I know / everything I want to find. Step 2 is to use, or to write out the equation I'm wanting to use. in this case, we're trying to solve for my r here. And so we're going to use the formula we actually just introduced a couple of seconds ago. And we said r, r is equal to v divided by I. Okay. Our third step here is to plug in all of the values we know. So we have r is equal to 9 volts over 0.006 amps. And our last step is we're going to plug that into our calculator, and we get 9 divided by 0.006. We should get 1,500, and we have units there. We're going to box our final answer, and we're going to call it a day. So here, just again, first step here, we wrote down all of the values that we knew and the value that we're looking for. Doing this makes it super easy to determine what equation we're going to be using, right? If we aren't looking at specifically our resistance notes, which in this case we are, hopefully we know that we're going to be using the resistance formula. But say you got this this question and you were given all of the equations. Sometimes the question is, what equation do you use? But by going through step 1, we know we have V, our voltage, we know we have I, our current, and we know we want to find our resistance, R. We look at all of our equations and say, which equation involves V, I, and R? And from there we go, it's this equation. Right? So by writing it out at the beginning, it helps us determine what we should be using and when. Okay? Then we're plugging in our values in step 3, and our final answer needs to have our units, right? And resistance is measured in ohms, so we need to include that. Alrighty. Next example, we have a TV is operated by a 26 volt generator. The current has a resistance, the circuit has a resistance of 68 ohms. What amount of current can pass through the circuit? So again, step 1, we are going to write out what we're given, what we're looking for. So we have this value given to us, we have this value given to us, and we're looking for the amount of current. Okay, so 26 volts is actually our potential difference, our voltage. We know that because of the units. We have 68 ohms, and we know resistance has the units of ohms. Oh my goodness, here. I'm having zooming in issues today. 68 ohms, and that is my resistance. And I'm looking for my current. I am looking, all right. Resistance, 68 ohms. And I'm looking for my current. And I don't know what it is, but I know that it's measured in amperes. That is my unit for my current. Okay. My next step is I'm going to write out the equation that I'm going to be using. Just as a side note here, I'll do this in purple. We know that resistance is my voltage over my current. I need to rearrange this formula to solve for I. I should have I is equal to something. Remember, if we want to use our triangle, V goes on top. And to figure out what I is, I cover up I. Oops. So I is going to be equal to V divided by R. So that is the formula we'll be using. So that's step 2. I is equal to V divided by R. Step 3, we are plugging in all of the values that we know. So for voltage, we know that's 26. For resistance, we know that's 68. Oh no, 68, come on. Woohoo! And our final and last step here is we use our, sorry ladies, having some technical difficulties here. We plug this into our calculator, we go 26 divided by 68, and we'll round to 2 decimal places here. So in your calculators, you should get 0.3823529412. If we round to 2 decimal places, we're looking at our third decimal. Because it is a 2, we're going to round down. So we should get 0.38. And of course we need our units. And since this is current, our units are in amps. We have a box around our final answer, and we are going to call it a day. So 0.38 amperes of current will pass through the circuit. All right, we have one last example, and then there is going to be a worksheet for you to practice with using all of this new equation that we've introduced today. So this last one, if you're feeling pretty good about yourself, please pause the video, try it out on your own. Once you unpause it, I'll be here doing it with you. But just test yourself, see if you could give it a shot, okay? I believe in you. Did you pause? I hope so. All right, welcome back. We have this last example. We have a laptop is operated with a current of 6.7 amperes. There is a resistance of 17 ohms. What is the voltage of the laptop's battery? Okay. So again, we are going to start off by writing down everything we know. We have the 6.7 amps here, and we have these 17 ohms over here. So 6.7 amperes, we know that current is measured in amperes, so that is an I. We have our 17 ohms, and we know resistance is measured in ohms, so that is an R. And we are looking for the voltage, or the potential difference of the laptop's battery. So we are looking for our capital V, which we don't know what it is, but we know that it has the units of volts. Okay, so we'll have some amount of volts as our final answer. Next, we have to find an equation that we're going to be using. We need to have V is equal to something. We know that we have a formula for resistance that involves resistance, voltage, and our current. But we need to rearrange it so that it's V equals something. And if we use our trusty triangle here, and we're looking for V, we're looking for voltage, so we'll cover up V, and we end up getting V is equal to R times I. Okay, so that's the equation we will use. We have V is equal to resistance times our current. Step 3, we'll plug in all the values we know, so it'll be 17 times 6.7. And for our last step, we're going to plug that into our calculator. We're going to have units there as well, so we have 17 times 6.7. We should get 113.9, and our units are volts. Put a nice little box around our final answer to indicate that we are done here. Alrighty. So that is it in terms of our resistance notes. Coming up next, you will have a worksheet to get practicing on. The answer key is already posted for you to take a peek at. Try your best. Make sure you ask me if you have any questions. Otherwise, that's it. That's all for today. Have a wonderful day, and I'll see you soon. Bye.